now let's start with the robotics. So from today, we will start to talk about the robotic analysis based on mathematical modeling. So before we go into the real robotic analysis, so let's start with some basic concept, which is the transformation. Okay, so why we talk about transformation and why this is very important to the robotic analysis. So let's see something. So let's take a look at this figure. So for example, the one on the left, if we take a look and let's do a quick analysis about the joints it has. So right here, this robot, and we can see right here, there is, obviously that is a revolute joint. So it means the robotics can rotate in this direction. Okay, and it can rotate around the z-axis. And right here, there is another joint. And this joint is, obviously, that is also a revolute joint. So let me say it R for revolute joint. Okay, so here we have the second revolute joint. And if we draw here the z-axis, let me call it z1. And this z1 is for the rotation axis of the second revolute joint. And if we define the space of this revolute joint, so that we will have x1 and y1. Okay, and then we take a look at here, we have the third revolute joint. So again, if we want to define the coordinates, the frame to define this joint, so here we will have z2, and apparently we will have x2 and y2. Okay, and right here we have another revolute joint, so it means that you can define another coordinates to define this link. So why we do that? Why we do transformation in robotics analysis? It is because all of these, we can see that robots is a combination of joints and links. So each link actually can be represented by a coordinate system. Okay, so if we consider this thing, the x, y, z, that is, we call it the world coordinates, the world coordinates. It means the basic coordinates in the real world and for the base of the robotics. And also, it depends on how many joints we have in a real robotics. So we have 1, 2, 3. In this case, we have 1, 2, 3, 4. Actually, we have 4 joints in this robotic arm. And the base revolute joint, we are using the universal, which is the world coordinates. And then the second revolute joint, and we define a joint coordinate. And here we have a joint coordinate, and here we have a joint coordinate. So in total, we have universal coordinates. And for each of these joints, we have joint coordinates. Actually, for each link and for each joint, we have a new coordinate system to represent each joint with the following link. And finally, here in the end, again, what does this called? What it called and effector, right? And which is the tool. Okay, so at this end effector, we also need to define another coordinate system, and this final end effector coordinates, that is the final workspace coordinates, right? So the workspace, what does workspace mean? And the workspace, it means the whole space, the end effector can swipe. Okay, so here we also need to define the coordinates for the workspace, that is actually the coordinates for the end effector. Okay, so then if we take a look at this robotic arm system, we have the universal coordinates, which is representing the world coordinates and is also the base coordinates. And then we have all these joints. So each joint, it has a new coordinate system. And finally, we have the workspace coordinate system. So, and then the question is, why we use a robotic arm? What is the goal of the robotic arm? So the goal actually, it means what we want the robotic arm to do. So for example, if we want the robotic arm to quickly grab a cup of tea, so for example, and we have to carefully control the motion, and we have to well plan the path of the end effector, which is the hand of the robotic arm. Okay, and another example is if we want the end effector, which is right here, if we have a pencil, for example, we want the robotic arm to draw something, and then it means we have to carefully control the coordinates that this thing, the end effector, can draw, right? So each of these points, that is a coordinates, means we have x, y, and z for each point that we need to draw. Okay, so then it goes back to the whole robotic system that we can control each of these joints, because each of these joints is controlled by a motor. So it means that we can program, and so that we can control the motion. And then it goes to, finally, we want the goal to achieve the goal of the robotic arms. So it means we have to carefully control the series of these x, y, and z, these points, so that we can exactly give at each time t what is this point. Okay, so it means that we have to understand all these coordinates very, very carefully. So that's why we need to do these transformations, because between each coordinate systems, we're actually doing a transformation. Okay, so the goal is we want to control the workspace, means we want to control all the coordinates of these points that can achieve by the end effector. So then let's start with some concepts. Okay, so the first thing we need to know is position, and position, that is obvious. Okay, so let's take a look at a point, which is this blue one, and this point we called it P. So we have a point P, and this point P is in the A frame. A frame means the A coordinates. Okay, so we use a bracket with A to show that this is a frame, and it means it's a coordinate system. Okay, so we have this XA, YA, and ZA. So here, this A right here, it means the reference. So it is written as XAA. It means XA with the reference of A. So it means just this axis. Okay, so now we have this P in the A frame, in the A coordinate system. Okay, and because it is in the A frame, so we write as PA. So right here we write as PA. And if we want to know the position of this point P in the X, Y, and Z in this A coordinates, we can quickly give by PX, which is right here, PX, right? And PY, and which is the projection to the Y-axis, and PZ, which is here, right? PZ. Okay, so we have PX, PY, and PZ. So then these three means, okay, the final position of P in the A frame. Okay, so we have the thing. And XAA, it means the unit vector. This means the unit vector. The unit vector means the length is 1 and it is in the desired axis. Okay, so XAA, it means in the x-axis, in the a coordinates, so that is written as 1, 0, 0. Okay, and because because this is x. Okay, here we have x, y, and z. And why y is 0? Because x, the unit x, which is right here, and this is 1, the length is 1, and this is XAA. And if we consider that, and in the a coordinates, the x is obviously that is 1, and the y, because this is on the x-axis, that is perpendicular to y, so the projection is 0, so we have 0. And the projection to z is 0, so the unit vector means at the axis it is on, and that is 1. If it is not, that is 0. Okay, so YAA, it means the y unit vector. The y unit vector, so here again, this is x, and because this is y, so y is 1, and x and z, they're 0. Okay, and ZAA, obviously here x is 0, y is 0, this is z, so z is 1. Okay, so that is the definition of unit vector. So now we consider this P point in the A frame, in the A coordinate system, and the position of this P, that is Px, Py, and Pz. And now in this XAA, YAA, ZAA, and PA, they're all in the A frame. So now let's see what is Px. Okay, and Px, if we want to use the unit vector to calculate Px, and that is obviously, that is the P, which is right here, that is projected to x, right? Projected to x. So then we write as this formatting, that is for dot product. Okay, and what does dot product mean? That means projection. Okay, so it means when we want to calculate the Px, which is, remember that we have this point Pa right here, and it is equals to Px, Py, and Pz. So if we want to calculate Px, Py, and Pz, that is this P projected to x, so we have Px, and so this is Px. And if it projected to y-axis, so that means this vector dot product with the unit vector of y. So then that means it projected to y. Okay, so it is this Py, and then we're doing the projection of this P to the z-axis, so we have this Pz. Okay, so we can see that if we want to calculate the position of the point P, we can actually do a projection to x, y, and z-axis. So this is how we define the position of a point P in this A frame, in this A coordinate. And again, this formatting, it means the dot product. Okay, that is the calculation of dot product. So finally, what is this? This is a number. So it means Px, if we calculate this vector and this vector, they do dot product, it means this is actually you're gonna have a constant, because this thing plus this thing plus this thing, the number, and finally this is going to be a sum, which is a number. Okay. So then let's think about, now we have another coordinate, okay? Like in the robotic arm, and we were showing from one base, and so here, for example, here is the base, and base we have the arm, and right here we have the revolute joint, and we're connecting to another link. So in the world coordinates, we have this z, and we have this x, and we have this y, and then right here, because we have a new joint and this joint coordinates, and here we define the rotating axis. We always define the rotating axis as z. So let me call the z1, and here we have x1 and y1. Okay, so we can see that in the real robotic arm, if we want to consider the motions transformation from the base to the next link, so we need to compare these two coordinate systems and see what is different and how they achieve the rotation and positioning. Okay, so we start with the orientation. Okay, so here is the basic concept of, let's forget about it. Okay, so let's forget about this thing. We'll just talk about the basic, and this is the motivation why we do this rotation. Okay, so now let me just rotate. Let me just erase the thing. Now we just focus on the math. So now we have a A-frame, and we also have a B-frame. B-frame is another frame. So if we want to use A-frame to achieve B-frame, how we're going to do that? So we need to do 2 steps. Okay? And the first step is that we need to rotate it, right? And here we have the A-frame and we have the B-frame. So if we want to achieve the B-frame, so let's do the rotating first. Okay, so if we do the rotating, okay, so we will have this B. We rotate it to the angle that is B first, and then we move it to B. Okay, so we do 2 steps. One is rotation, one is positioning. And we also call it translational motion and or offset. It means we just move the whole thing, we move this whole thing to this part. Okay. So then the question is, if we want to rotate from the frame A to frame B, what is the rotation matrix? How we're going to use some math modeling to understand the rotation. Okay, so here we define the rotation matrix R, A, B, and here if we write up, A is here and A is the reference. So now the rotation matrix means, okay, so in the X, B, Y, B, and Z, B, what are the projection that is in the frame A? So that means the rotation. Okay, so if we take a look at these 2 frames, so actually XA, XBA, that means, okay, so let's see what is the unit vector of B. Okay, so now if we just take a look at the frame B and we define 3 unit vectors in the coordinates B, and here we have the thing that is called X. If we only consider this unit vector in the frame that is supposed to be, we write it as XB and with the reference of B, and here we have the YB in the frame of B, here we have the ZB in the frame of B. Okay, so then what does XBA mean? It means, okay, so now my XB, what is my XB with the projection to A? Okay, so what is my XB? So if I just parallelly move the thing to the A frame, so right here, it means if we move it to the A frame, here we have the XB, B. Okay, and what is the vector of this thing with the reference of A? So this is XB A. We consider this vector, which is the unit vector of XB in the A frame. Okay, So if we can consider the orientation from the B, the unit vectors of the B frame, we consider 1, 2, 3, which are X, Y, and Z. We consider these 3 unit vectors in the reference A frame. So then we will be able to calculate orientation, right? So that is, we consider all the projections of X, Y, and Z in the A frame. That is how we define the rotation matrix. So that is the XB in the A frame, YB in the A frame, and ZB in the A frame. Okay, so the question is, what is XBA? Okay, so by definition, this is the projection, right? The projection. It means how we project XB in the A frame. So then that is the XB, the projection is projection to the A axis, to the X axis in A, to the Y axis in A, and Z axis in A. Okay, so if we take a look at, so here this thing that is XB A, and if we consider the projection right here, that is the projection XB A with the unit of A, so that is XA A. Okay, so that is projection. So it means if we want to do the projection of X, of XB A, and in the A frame, that means we have to do it as it projected to XAA and YAA and ZAA. So this is, again, this is a number, this is a number, this is a number. So again, this is the dot product, okay? Dot product. And so finally, the rotation matrix of B with the reference of A, that can be calculated by the XB projected to A and YB projected to A and ZB projected to A. Okay, so that is 3 projections. So there are some properties of a rotation matrix. There are some properties. And first of all, that is the inverse of a rotation matrix. The inverse of a rotation matrix is its transpose. So why is that? It is because we can do the calculation. So here, if we calculate the RAB and that the transpose of that, multiply the RAB, the original RAB, then it's going to be the transpose multiply the original RAB. And so that is, we do the transpose and then we do the original vector. So then we have the calculation of these two. So then if we do the matrix multiplication, we're going to have this final matrix. So if we take a look at this thing, YAB dot product with YAB, so these two are the same and they're the unit vector, so these two are the same, so we have 1 here. Okay, and these two and the dot product and XBA and YBA, and they're both XB and YB, apparently they should be perpendicular to each other, so this is 0, and again this is perpendicular, so this is 0, and here I have 0, 0, and here this 2 is the same, and this is the same, so we have 1, 1, and all the other terms, they're 0. Okay, so it means that the thing, these two, the transpose and the original matrix, they are doing multiplication, it equals to this unit matrix, so it also means that this is the inverse. Okay. And then remember that when we consider two frames, from one frame to the second frame, from here in this case, that is from A to frame B, we always consider two steps, right? Two steps. One is the rotation, which we just talked about. And then the second is the positioning. It means the translational motion, Okay, so in this case, we have done the rotation and then we do the positioning and we call it P and with A. So this means this vector from A to B. Okay, and this is B R O R G. It means PB, the origin of B, which is right here. Okay. So if we do a mapping from frame to frame, and we have to do two steps. Again, we have to do two steps. One is the rotation. One is the rotation from A. We rotate it to B first, and then we move it to the new location, which is right here. Okay, so the mapping from frame to frame, we need to do two things. The rotation R, A, B, and then it goes to the position P, B, that is the motion of origin and with the reference of A. Okay, so here, so far, until here, if you cannot understand exactly the mathematical calculation, it is fine. Because in the following lectures, we will go into the very details to talk about how we're going to calculate these rotation matrix and these position matrix. So at the first class of robotic analysis, I just wanted to show some basic concepts, and especially this transformation concept and how we're going to convert one frame to the other frame, and then maybe to the other and to the next. Okay, and next week, the lab session, we're gonna do the visual recognition. So it means that if we use a webcam to capture our face, and we will be able to track the orientation of our face. So why we can do that? It is because in the camera we have a coordinates, and in the real world we have the world coordinates. So how we're gonna do the transformation from the world coordinates to the camera coordinates, and so that is also another application of the transformation, the coordinates transformation. So actually the idea of matrix of coordinates transformation, that is widely used in all these type of analysis. Okay, so here let me just quickly go over what we're gonna learn in the following 3 weeks. Okay, and here we're gonna talk about the projection, which is, here is the rotation plus the position. And finally, we want to use a uniformed transformation matrix to represent both the rotation and position. So that is called homogeneous transformation. Okay? So that is here, this T right here, and that is, we call it homogeneous transformation. So don't worry about these mathematical calculation, and we will go into the details, and we will do a lot of examples in the following lectures. So don't worry. Okay. So then let's start with the homogeneous transformation. So let's go with the robotic analysis. Let's go into the details. Okay. So why, again, the motivation of that, why we do that? So if, again, we show the robotic, in the beginning of this lecture, we show this robotic arm, and we show this robotic arm, and this is, again, this is the base, and the base is able to rotate. And here we have a revolute joint, and we have another revolute joint. Okay, so it seems like it's a robotic arm, and it can rotate and it can rotate. So again, the motivation of the transformation calculation is that we need to understand the motion from one coordinates to the other, to the next, and to the next. Okay, so it means we need to know the kinematics of the robotics. So when we understand the transformation between these coordinates, that is the kinematics. Okay, so again, that is the position plus the orientation, so 2 steps. So both the rotation and the translation, and which is positioning, are important. And of course, the homogeneous transformation, it shows a homogeneous method to combine the 2 operations in a single matrix multiplication. So that is easy for the following kinematic analysis. Okay. So then let's start from the very beginning, from the 2D. And previously we showed the concepts of the transformation. So now let's go into the calculation. Okay, so let's start to calculate it. Let's start with the position. So what is the position? The position is, okay, so here we have these 2 coordinates. Let's start with 2D. So this is 2D. We have the first x0 and y0, and then we have the second frame, and let me call it frame 0, and this is frame 1. And so we have this x1 and y1. A coordinate frame, the thing, it consists of one origin, which is right here, and this is 2D, so that is x and y axis. And so if we consider a point in the space, and this P, if the P is in the coordinates frame 0, so then the position of that is, this is x and this is y, right? And this is px in the 0, and this is py and 0. So then the position of this P in the 0 frame, we write it as P0. So here the thing is Px, which is right here, and this is Py. And from this drawing, and we can quickly measure, this is 5 and this is 6. Okay. So then how about this P point, which is right here, this P point in the frame 1. Okay, so if we want to do that, and obviously we need to consider, we just forgot about this 0 coordinates, which is consider the position in the 1 coordinate. So then we have this Px1, right, in the 1 frame, and this part is Py1. Okay, so if we do a quick measurement, and this thing, that is obviously that is negative, right? This is negative, so that is negative 2.8, and this part that is positive, so that is 4.2 based on the measurement. Okay, so we can see that when we consider one point, the point, if we talk about the position of a point, we need to know that what is the reference frame we're talking about. If we talk about the frame 0, it means the position P in the frame 0, then we have this position vector of P. And if we consider this point P in the 1 frame, so then this is the position of P. Here comes to the second question. So now we have this origin of the first frame, so let's call it origin, so we call it O0. and here we call it O1. That is the origin of the frame 1. Okay, frame 1. So then my question is, what is the position O0 in the one frame? So if we want to do that, we have to find, okay, so here is my x1 and this is my O1. If we want to consider the position of O0 in the frame 1, so this is my O. If we write the position of that, that is O0 in the frame 1. So again, this is reference. So then this thing from here to here, that is pretty long, and if we measure that, that is negative 10.6. And if we consider the y, and here this is going to be my y, so then it means my origin of the first frame, which is frame 0, in the position of that in the frame 1, we will have this vector. Okay, and if we consider the O1 in the frame 0, it means we need to consider the position of O1 in the frame 0. So then here is my projection, and here is my projection, here and here. So this is, if we measure that, this is 10, and we measure that, that is 5. So it means if we consider the O1 in the frame 0, we will have this vector. So that is the position. Okay, so the next concept we need to know is vector. So vector, and I want to say that a point corresponds to a specific location in the space, which we just talked about it. A vector, it specifies a direction and a magnitude. Okay, so here we have the point P, and we have the location of the P in the frame 0 or frame 1, which we just calculated. But the vector from O1 to P, we define this vector as V1, and we want to say that we want to know that the point P is not equivalent to the vector V1, because the P means the position of P in the frame 0, but the V1, it means the origin O0 to the point P given by the vector V1. So that is the displacement from the origin O0 to P. So point P and vector V1, they're different. Although it may look the values may be the same. So let's see the position of vector. Okay, so here we have V1, and this V1 is from O0 to P. If we use the reference of frame 0, then we write it as V1. Here we have the V1 and with the reference 0, and apparently that is equals to the P vector. Okay, so here this is my 5 and this is 6. And if I consider my vector V1 in the one frame, in the frame 1, it means that, okay, so here I have my V1. If we want to consider the reference of 1, so it means we have to move it to this coordinates first, and so here is going to be my V1, and then I will have my vector V1 with the reference 1. So then here the thing is 7.77, and this is actually pretty small. That just 0.8. Okay, so if we parallelly move the thing to the frame 1. Okay, Then let's take a look at V2. Again, by definition, what does V2 mean? V2 means the displacement from O1 from the origin to the point P in this frame. Okay, so here is my V2. Okay, so if we consider V2 in the one frame, which is right here, and then apparently this is my V2 in the one frame. So here that is negative. So measure that, we have negative 2.89. And this is positive, and this is positive, so that is 4.2. Okay, and the last one is V20. So V20, it means my vector V2 in the coordinates 0. Okay, so I parallelly move my V2 to here, and again this thing and this thing, these two should be parallel. Okay, so if we move it here to the frame 1, so we're gonna have this is my, and okay, sorry, this is, now we have, sorry, okay, you erase it. So my V2 0, because the reference is 0, so we should use x0 and y0, so it projected to x0, so this part is negative, that is negative 5.1, and this is positive, that is projection to y0, so that is 1. Okay, so that is how we consider the vectors with the different reference frame. Okay. So the vectors is the manipulation of vectors. They need to be defined in one coordinate frame. Okay, so it means if we give a vector, we have to name the reference. So for example here, and we give this vector, and we cannot say it's V1. If there are two coordinate systems, we have to say V10 or V11. Otherwise, we cannot tell what we're looking for. So we need to give this reference. So for free vectors, they can be defined in parallel coordinate frames where axes are parallel. And so here, if the references are different, so for example, V11 and the reference is 1, and V22, the reference is 2, is not defined. So we cannot do the sum of these two, since the two frames are not parallel. So we cannot do the calculation of that. Okay, so since this is not be able to calculate it, so that's why we need a transformation, so that we can do a lot of transformation. So once we have this transformation, we can do a lot of calculation like that. Okay, so again we do two steps of transformation: rotation and translation. That is positioning, translation. It's also called positioning. So again, we start with the rotation. Okay, so in the previous transformation, mathematical transformation, we just talked about, we saw those two frames A and B, and we saw the rotation. So now let's start with the calculation, okay? So again, we start from 2D. It's easier to understand. So let's take a look at these two coordinates. So here in this 2D, we have x0 and y0. If we do a quick rotation and we rotate theta, rotate theta so that we have a new coordinate that is x1 and y1. So then what is my rotation matrix? Okay, so my rotation matrix, actually it means the coordinate frame 1 with the reference of coordinates of the coordinate frame 0. Okay, so the rotation matrix can be found by defining the unit vectors of frame 1 with regard to frame 0. Okay, so if we want to calculate the rotation, this rotation from x0 to x1 from frame 0 to frame 1, if we want to calculate the rotation matrix, so we write as R1 0 because 0 is my reference. Okay, and this rotation matrix can be calculated by, remember, we just talked about it. We just talked about the 3D rotation in between A and B. So how we did it? Okay, we did the projection, right? We did the projection. So it means that we need to do the projection of x to 0 and y1 to 0. Okay, so if we write down that, what is that? That is actually the dot product of x1 to 0, right? So if we write that, it can be x1 dot x0, x1 dot y0, x1 dot z0. And again, here these x1 and x0, y0, z0, they're all unit vectors. Okay, and then we need to do y1 projection to the 0 frame. Okay, so we have y1 dot product. Again, dot product means projection. So dot product we can write as dot product, or we can write as this type of formatting. Okay, so we write as dot product, so it's y1 projected to x0, y1 to y0, and y1 to z0, which we just talked about it, right? It means the x1, the unit vector x1 projected to x0, y0, and z0, and y1, the unit vector projected to x0, y0, z0. Okay. And so this is a vector, and this is a vector. So here it means a vector. And then let's take a look at, oh, okay, so this is 2D, so there is no z0, sorry. There's no z0, okay? There's no z0 because that is 2D, okay? So we only have x0 and y0. They're all unit vectors. Okay, so then let's take a look. One method to calculate this x10 is to think about the projection. Okay, so then if we take a look at the thing x1, here is my x1 and here is my x0. So what is the dot product of x1 projected to x0? It's this thing, right? This thing. And again, my x1, x0, x1, y0, y1, x0, y1, y0, again, they're all unit products. It means the length is 1. Is 1. Okay, the length is 1. Okay, so then it means if we do the dot product of x1 and x0, the dot product, that equals to x1 and x0, the dot product, it equals to x1. If we don't know the coordinates, we just know the vector, that is, the absolute value means the length times the dot product means times cosine the angle, right? And because these two are unit vectors, so this is 1 and this is 1, so we only have the cosine theta left. Okay, so it means this x1 dot product x0, that is finally equals to cosine theta. So here we have cosine theta. Means here we have cosine theta. So the next term is x1 dot product y0. So here I have my x1, and where is my y0? And here I have my y0. So again, my x1, my length is 1, and the length of y0 is 1. So it means that if we want to calculate the dot product, we have to consider this angle. So it's going to be cosine. So it means my x1 dot product y0, it is 1 times 1 times cosine this angle. The cosine this angle equals to 90 degree minus theta. So cosine 90 minus theta, what is the value of that? That equals to sine theta. Okay, so here I have my sine theta. So that's why this thing right here, this term equals to sine theta. So here we have sine theta. So these two, let's compare these two. Okay, so this term that is y1 dot product x0, again, since these two, the length is 1, so we only need to consider the cosine of the angle, Here I have my x0. Where is my y1? And y1 is here, so this big thing is my angle. So that is 90 plus theta. Okay, so it means is cosine 90 plus theta. So that is negative. Sine theta. And the last term is y1 dot product y0. So here I have my y0 and here I have my y1. So if we do the dot product, again, finally it equals to this angle. This angle is theta, so it directly equals to cosine theta. Okay, so we can see that if we want to consider the rotation between two frames, we need to calculate the rotation matrix, which is R10. R10, it means we have the reference of 0, and we rotate to 1, frame 1. If we want to calculate it by definition, as we just talked about 20 minutes ago, that is my new frame projected to the reference frame. So that is x projected to x0, y0, y projected to x0, y0. Okay? So then we have, by definition, we'll have these 4 dot products. And then my question is, this is 2D, so we have x and y, so that is 2 times 2. So if it is 3D, and that is going to be 9 terms, so it's going to be 3 times 3. Okay. So the rotation matrix defining the orientation of the frame 0 with regard from the frame 1. Okay, so we just talk about it. Okay, so now we can see that here is, again, it shows these matrices, these dot product, so that finally we have this R10. So here, again, 0 is the reference. So if 0 is the reference, means the 1 projected to 0. So here, 0 is the base. So we write as x0, y0. And here we also write as x0, y0. So this is the definition. So this is very, very important. This definition is very important. That is the projection by dot product. Okay, so then we goes to the R01, means 1 is the reference. Okay, so we have the reference right here. if we consider the reference right here, and then this means my 0 projected to reference 1. So here we can see that here becomes the projected to x1, y1, x1, y1, and here is x0, y0. Okay, so if here we have the reference, it means what is my base?